finish up. We're going to finish up forces real quick. We're going to solve. We're going to solve what amounts to be probably the hardest type of forces problem that you'll see on the exam. Well, for most of you anyway. Incorporates most of the stuff we've talked about with forces. So let's do that real quick. And then we'll talk about circular motion. Okay, so we're going to start like this. We're going to do... All right, so here we go. This problem, here, let's do this first. Let's say that first, we're going to cover everything. First, this is attached to a spring that's attached to a wall down here.
Oh, no.
Okay? All right. First off, we have two masses. Mass M. Put that other subject away, Rudy, or I will shred it.
Shred it right there, ready.
No, right there.
No,
Hey, listen. I don't expect you to do physics in anybody else's class, so don't do anybody else's class in mine. Okay? Deal?
Deal.
Oh, this is like an oddest situation. Why would you ever?
What?
Why would anybody ever make something like that?
Because it's a physics test, and they make all kinds of crazy things. Crazy contraptions just to see if you can figure it out. All right?
Because you want to get the mass up with kilos, you know, like little bitty things like a small spring.
If you ask why, then you won't solve it. So don't ask why.
Because you randomly pull that stuff out of your pocket and set it up.
All right, so this is K. Spring constant K. Incline, angle theta. There is friction between these two and a mass M. And we have a frictionless, massless pulley of science and a magical, massless, non-stretchy string of science connecting them, and a magical, massless, linear spring of science. All right? And there it is. So first things first, it's stationary. So what I want to know is, question number 1, is how far does the spring stretch? Okay? From its normal equilibrium position to hold it like that. All right?
Go?
Okay.
Okay.
All right?
Is there no friction between the one on the left and the side of the...
What's that?
Okay, never mind.
No, we're not.
No, there's no friction here.
Okay.
And let's also assume that if the spring wasn't there, well, let's just figure it out. Which way would it want to move if the spring wasn't here?
Down.
Okay, which way down? This way down or this way down?
This way down.
To the right.
Clockwise or counterclockwise?
This way.
Clockwise.
Clockwise.
Clockwise, so if I get rid of this spring, it's going to go this way?
This heavier.
Well,
Oh,
no, you
it's
said it
bigger.
was stretching. Well, how big's the mass?
Yeah.
It's big.
That's M and that's M.
They're both the same.
They're not gonna move.
Are they the same?
No, yeah, they would,
That
but the
one
Y
looks bigger.
component's not
Are
the
they the
same
same?
as...
Okay, hang on. Let's think about this. If I had this situation.
Oh, yeah, well, it depends on where the equilibrium point for the spring is.
No, wait.
No, he
It-
said
They're
we're
both
down.
very similar.
Okay, look.
Oh, well,
Let's assume there's no friction. Shh. Assume there's no friction. Same mass. If I let it go, which way would it move?
Slightly upward.
no.
Well, the other one. This one goes up. Yeah.
Counterclockwise or clockwise?
Counter.
Counterclockwise. Okay, now, if there is friction, which way will it want to move? Now, it might not move if there's enough friction.
Yeah.
But which way will it want to move?
Same direction.
Same direction.
Same direction. Okay, if I add a spring onto it, which way will it want to move?
Upward.
Still this way, right?
What is this?
That's the way it's going to want to move.
Oh, it's flashing.
And we're going to assume Now they may ask you a question of, what's the minimum friction so that it won't move? We'll handle that in just a minute. But for right now, let's assume that it will move, okay? Let's assume that it will move. And I want to know, how far does this thing stretch? If I was to cut this or disconnect this spring, let's assume that it would move. So the spring keeps it from moving. Does that help out?
Yeah. Force
All right.
it to
So, we have to draw free body diagrams. So, I want you to draw the free body diagram of this mass and of this mass. Okay, what do they look like? Draw them, check with your neighbor, make sure you got the same answer. It's not moving, it's stationary right now, so it's at rest.
I like how there's a.
Okay, force is right here. What is it?
Down, straight down, and up. Tension.
Yeah.
Okay, what about this one?
No more force
Gravity.
perpendicular.
Gravity straight downward.
Tension.
Tension to the, yeah, and then spring to the.
Tension to the yeah.
Because I'm cool like that.
Tension to the yeah.
Just like you were the,
yeah.
the siren. See, at least I deciphered it. See, you haven't deciphered mine.
Is there friction?
Very nice. All right, is there friction?
Yeah.
Oh, rats, we forgot one.
Yes.
Oh, friction force.
Static.
They reminded me of the other
Static,
one.
yeah.
Spring.
There's friction force. I said there was friction. Which way would friction be?
With the spring one. Spring.
Okay, is it in the same direction as the spring or is it in the same direction as tension? Because it's got to be one of the two.
Spring.
Okay, it's wanting to move this way,
So it's other way.
so it's going to be this way. Force friction. Okay, everybody see that?
What's MS? Force spring?
Force spring, force friction. Okay, we can't make it much harder than this, right? Unless we submerge the whole thing in water and put buoyancy force on it all. Or put charges in them. Now we have electric cords.
You said you put charges in and then put a magnet just in the middle of the wrench.
That's right. Put a magnet right here
That's
and
like, that's awesome.
charge.
Yeah, that's pretty.
All right, now, it's stationary. Hey, it's stationary. So, what does that tell you about this? That one equals that one. Well, what's this and this? They have to be equal. It's stationary, so what else do we know? Okay, we got angle forces here, right? So which way do we break these up? What's our coordinate system over here? Like this, right? So we have to break this one up into components. So this one equals this one. Hey, boys. This one equals this one. This one equals this one.
That equals what?
That one equals.
And normal equals this component.
And all three of those.
And very nice, I got 3 right here. These 3 must add up to be
Tension.
that one. So if I would say tension equals force spring plus force friction plus mg
X. No, wait.
Sine.
sine theta.
Oh.
Very nice. mg sine theta, right? Because this is the theta right here. Okay? All right, so if I want to find spring force then is just tension minus the force friction minus mg sine theta, right? Let's move this junk to the other side. All right? We good? Can I do any better than this?
You can simplify friction.
If I get normal for it.
Oh, I could plug in mg for tension. Very nice.
Oh, right.
So I could plug in mg. Very good. So I have mg here. Can I do any better than this?
Yeah.
UFN.
Mu.
UFN.
Well,
Why
less
not?
now because it's static. You can.
It's equal to normal.
As if it were
Okay,
maximum.
what kind of friction is it?
That's
Static.
Static. So
Greater than.
it's greater than or less than or equal to mu mg, right? I mean mu force normal. Sorry. Okay, so
What
I
if,
can't.
what if it's not mu sub k but mu sub s?
Still, it doesn't matter. All right, so this is as far as I could go, and I would be almost done. And if I wanted to know the x that the spring would stretch, then what do I do?
Divide by K.
I plug in Kx and I divide by K and I'm done, right? Okay. Now that can't really get a whole lot harder. That's a pretty complicated problem because it has quite a few forces.
Like Lauren said, this whole thing could be in free fall.
Lauren, stop. We have a stationary incline of science. I said it was at rest. We can't. Okay, now let's make it into a dynamic problem. Now we get rid of the spring. And now my spring goes away. Okay, when the spring goes away, it's no longer at rest. I'm going to assume that it moves. Wait, let's not assume that it moves. Let's assume what is the minimum coefficient of friction that will hold this in place? The minimum coefficient of friction, that would be static coefficient of friction, that would hold it in place. What changes here in my free body diagram? Anything? Okay, that goes away. But it's still stationary, right? It's still at rest.
So now tension equals to rest.
Okay, so will you please calculate what the minimum coefficient of friction is?
So that it's still at rest? So that it's still at rest?
All right. What's our critical F equals ma equation? Is it one over here? Is it one over here? Which one?
The one over there is
The one right here that's this way, right?
critical technically.
Yeah. Okay, the sum of the forces equals ma in this direction, right? Actually, we're going to call that way positive. Probably. It's not accelerating, so that's 0. So we've got tension going up that way equals these two going down this way. So that's force friction plus mg sine theta. Now, it's static friction, which is always a danger because static friction is equal to is less than or equal to mu force normal. But since we're looking for the minimum that'll keep it in place, then we're at this equal sign. So we can put in mu force normal equals mg sine theta. Oops, I put an equal sign there. Plus. All right. Can I do any better?
The normal force is equal to mg cosine.
Ooh. There's a couple things we can do. There are two things we can make this better. One is, Nia told me that normal force right here is equal to this part. So normal force is equal to, and here's how you get maximum points on the exam. You write, hey, normal force equals mg cosine theta. So you can plug that in. And what else can you put in? Well, over here, tension equals mg. So you got tension equals mg. So you can plug that in. So you get mg equals mu.
You have to like take out mg and put 1 minus sine theta over.
No, you don't have to.
But if we want to, we can do that.
Yes, you
I don't
can.
want to.
Okay, does that look right?
MGs can do that.
We can get rid of the mg's completely if we like. Okay, if we want, we can get rid of them all, and that's left with a 1 over here. So we get 1 minus g sine theta. Oops, no, not g sine theta. 1 minus sine theta over cosine theta equals mu, right? There we go. Now, some of you, maybe when you're in a hurry on the exam, you'll leave mg in here, and mg in here, and mg down here. That won't be counted wrong because you've gotten to a correct answer. Okay? So you don't have to make it mathematically purist, perfect, the way your math teacher would want you to do. All right? Because you're limited on time, and they understand that on the exam. All right? No, not unless something special. All right, now Last question of our hardest question you'd probably ever see on the AP exam.
Is it really?
This would be one of the ones that students will miss a lot because it's a lot of work, right? It just takes a lot of time. Figure it out. All right?
Talk about the whole thing being equal.
Okay, last one is what if? What if mu is less than what we just calculated?
Then it will move.
Then it'll move.
So it'd be kinetic.
So now they may give you a different number for mu, for kinetic, or they may just say mu is less than this value you just calculated in part B of the problem. And they say now calculate the acceleration of the blocks. So now calculate the acceleration assuming mu is smaller than what we just got here. All right? Yes. Yes. What's that? All right. Does our free body diagram change? Look. Does this change? Changes a little.
Oh, yeah, MG is not there.
Are these two the same still? No. Ooh, now this is something that really upsets students sometimes. These were the same when it was at rest, and these will be the same also when it's moving at a constant speed. But if it's accelerating, one's got to be bigger. And if it's accelerating down, mg's got to be bigger than tension. So riddle me this.
Riddle me this.
Riddle me this. Which one changed? Tension or mg?
Tension.
Yeah, because just because this thing starts to move doesn't change the Earth and the gravity force, right? So tension will magically get less.
The earth got fatter.
Okay, now, magically because, remember, tension is a lazy force. It's that stretching of the bonds in between the atoms. Yeah, there's a little gremlin inside go, oh, we're accelerating. Time to back it down. All right? So now you're accelerating this way. And now you're accelerating this way. So tension no longer equals these two either. But this tension here does still equal this tension here, right? We're in physics B where our pulley has no mass. And no friction. All right? So here you go, everybody. I want you to write F equals ma for this mass, tension, mg. I want you to write for this mass, you've got your mg, you've got your force friction, it's kinetic now, you've got your normal force, and you've got your tension here. I want you to write your F equals ma for that direction, and your F equals ma for that direction, for your coordinate system, okay? Everybody do those, because if that's the key. If you can write those, then the rest is algebra. Good. All right, come on. Write your free body diagram stuff. Come on.
Just F equals ma, that's all you want?
All I want is F equals ma. That's it. Because that's the key. Free body diagram has to be right. You got to set up your coordinate system. You got to decide whether it's accelerating or not, and then you write F equals ma, and that is the essence of all the physics. The rest is just algebra, which may or may not be something you like, but it's just algebra. All right, so here we go. What's our equation look like right here?
mg minus t.
Okay, why not t minus mg? Why is it mg minus
You're
t?
accelerating downwards. So
Because
we're
we're
saying that's
accelerating this
positive
way.
downwards.
So mg minus t equals ma. And that's it. Done. Okay, what about, which of the two of these is the easier of the two?
The y, yeah, the y. The perpendicular is easy. That one.
I think this one's easier. Why is this one probably easier? Why is this in equilibrium? Because it's not accelerating this way, right? Perpendicular. So that's 0. That means that equals that. Those are my only two, right? So that means the normal equals mg cosine theta. Done. Now, this one we have acceleration. So what does the F side look like?
Oh, no, there is no.
T minus force of friction.
No, but not in that direction. Minus.
Mg sine theta equals
All right. Not quite done. That is correct, though. I have 1 in the direction it's accelerating and 2 in the direction that it's opposite direction accelerating. That's why they're negatives. Okay, can I make any of this better?
the force of friction
Okay, that's mu force normal, right?
and force normal is equal to mg.
And force normal is equal to this. So I'm just going to go ahead and skip this step and go right to here. T minus mu mg cosine theta. That's my normal force. Minus mg sine theta equals ma. Now I can't do any better than that. Now what did I ask for? I asked for acceleration.
Yeah. Just divide by 9.
You did ask for that?
I did ask for the acceleration. So if I just divide this by m, that looks good, except
We don't know.
I don't know what t is. So how do I get rid of t?
So that is.
Substituted for MA minus
Yeah.
Yeah. T
yeah,
is
MG minus MA. T.
So I solve this for t, and t is equal to mg minus ma. So that goes in here, and oh my goodness, mg minus ma. Oh no, I got an a over here. Minus mu mg cosine theta minus mg sine theta equals ma. Ah!
put your M on one side.
Okay, I can move this to the other side. Actually, all the m's go away first. And then I can move this a to the other side, which gives me 2a on that side, right?
Divide by 2.
So I just divide the whole thing by 2. So I get g minus mu
Cosine
g cosine theta minus g sine theta divided by 2 equals a.
It really step out G. I mean, undistributed.
Oh, and you could undistribute g if you'd like. Your math teacher would love you for that. But on a test, if you want to leave it like that, you go right ahead because that is mathematically correct. Okay? Now that is a really hard problem, especially if that's on a test, right? So this is certainly not going to be a multiple choice. Oh, if this is a multiple choice question, what do?
Skip it.
You skip it, and then at the very end, if you have any time, you try to solve it, and if you run out of time, you write an answer down.
Don't try to
Right.
solve it.
If it's on the free response, they would have multiple steps in this problem. Okay? Like the first question might be, you know, if it's stationary, what's the tension in the rope? Well, the tension in the rope will be equal to this mg, right? Then they might ask, what's the minimum coefficient of friction? So you can solve that part. And one of the questions is certainly going to be, draw the free body diagrams, which we can do, right? So don't get intimidated, because this is probably going to be 1, 2, 3, 4, 5, 6. It probably won't be 6 points, but it'll probably be at least 4. And then finding t is probably going to be another 2. And then finding mu is going to be another 3 or 4. And then this last part is probably going to be a lot, right? But by then you've already gotten at least half the points, right?
Yeah.
So don't be intimidated by these problems. Just continue to go through and answer questions, okay? Because you can do it, all right? That's right, you got your 4 points. I'm going for 4. You got to get a little more than 4.
I got my 6.
Okay. I can't make it much harder than that.
Really?
I could, but I can't in this class.
Until we get to see.
Air resistance.
Yeah, in physics C, the complication they add is that the pulley has mass. And then we have rotational motion to worry about, and that involves something that we don't want to deal with just yet. Okay, this is plenty for physics B. Okay, but you will be able to do that when you get there. My students just got through doing that.
Let's do it in free fall.
Yeah, and then we submerge it. We are on to a new topic. Okay, your next test coming up, not this week, but probably the week after, I don't remember,
Yeah.
is going to include all of forces, so problems like this and stuff we had, plus circular motion. Okay? So, let's start talking circular motion. All right, first things first. When we have talked acceleration so far, we've been talking about change in speed acceleration for the most part. But there's another type of acceleration. There's an acceleration that gives you change in speed. That's called tangential acceleration. Tangential. Or sometimes it's referred to as linear acceleration. Okay? Tangential or linear acceleration. That's the kind of acceleration that changes your speed. This acceleration is parallel to the direction the object is going. So like for instance, if you had some object that is traveling in this direction, if it accelerates that way or that way, that is parallel to the direction it's going, this acceleration would make the object speed up. This acceleration would make the object slow down. Okay? All right. So we're kind of familiar with that. That's the acceleration we think about when we're doing kinematics for the most part. We're thinking about speeding up or slowing down the object, right? Now we're going to add a new type of acceleration. Our new acceleration is going to be called radial or centripetal or perpendicular acceleration. This changes the direction of the object. Listen up. Hey, listen up. If you accelerate perpendicular to the way you're going, if you accelerate that way, then what that literally means is, remember that acceleration is the change in velocity with time, right? If your change is in a different direction than the way you're going, then that's going to change the direction. Okay? Because if this acceleration, which is delta v over delta t, if that occurs over a certain period of time, then this is going to be my change in velocity, right? If I multiply this by time, right? So my velocity will change to be more in that direction. But I had an original velocity as it was. So my original velocity was this way. But my change in velocity is this way. So this will be my new velocity.
But every time it keeps changing.
So that's the deal. If that acceleration maintains that direction, then you'll get parabolic motion. Okay? So like for instance, think about it this way. When an object flies through the air like this, the acceleration is always downward. The acceleration happens to be g. Alright? But look what this does. The velocity right here is this way. Then the velocity is this way. Then the velocity is this way. Then the velocity is this way. Look what this does, everybody. Part of this gravity is perpendicular. It's a centripetal acceleration. And part of this gravitational acceleration is this way, which is, please stop, tangential. What's the tangential acceleration doing to the velocity right here? Slowing it down. What is the centripetal acceleration doing? Causing it to curve this way. Okay, look what happens at the very top up here if I drew it just right. Then if I drew it just right, then all of it is centripetal. So at the very top, it won't be changing speed. It'll only be turning, right? And then when you get here, notice that part of it is perpendicular again, centripetal, and part of it is tangential. What's the tangential doing over here? Speeding it up. And what's the centripetal doing? Turning it, right? Does that make sense?
Yeah.
That's if the acceleration is always in one direction. If the acceleration is always in one direction, which means that the force is always in one direction, because remember, F equals ma. So if the acceleration is always down, the force is always down, then you will always get parabolic motion. So look, here you go. Here's a little tie-in to electricity. If I have a capacitor plate here and here, and I put positive charges down here, and I put negative charges up here on the capacitor plates. And if I was to shoot a positive charge through these plates, which way would the positive charge get a force as it goes through? Upward, right? Because the plus would repel it and the negatives would attract it. So it's going to get a force up. As it moves through, that means it's going to turn upward, right? Will the force still be up? Yeah, the force is always going to be up on it, right? As it goes through. So this thing is going to go through here and curve upward. And that arc right there, guess what? It's going to be a parabola. It's going to be the exact opposite of what it looks like with gravity. Gravity, it looks like this. In this case, it's going to curve with a parabola upward. So this is like the car driving off the cliff, but flipped over. Right?
Is there a sneak number bed at the top?
That's right. So this would be like what would happen if we had anti-gravity. Right? You throw the ball and it would curve up instead of curving down.
The gyro ball?
No. All right.
Baseball.
Now, circular motion occurs a little bit differently. Circular motion, the acceleration continues to point towards the center the whole time, and there's no part of the force that's causing it to go into a circle that is parallel to the path. So let me give you a couple examples. Well, here, let me give you the easiest example.
He's happy in our
Because he's looking at Mr. Brewer, he's sad.
Oh, what the heck?
Oh, yeah.
All right.
What is this?
Hair.
Curling his hair?
This is coronas.
Oh, those.
Right. Here you go. Planet in circular motion. Which way is the planet going?
Whichever one you choose.
Ooh, now, everybody, this is really important. Hey,
It's elliptical, we're talking.
boys, pay attention. Circular motion. Which way is it going? If they ask you on the test, which they're likely to do sometime, to ask you which way is the direction of the velocity,
Counterclockwise?
you have two choices.
That way or that way?
Yeah, the answer is, but is it that way or this way, or does the vector have to be a straight line?
Straight line.
Okay, so how do you draw a straight line that represents the velocity? It's got to be tangent to the path. So it's got to be either up or down, whether it's going clockwise or counterclockwise. So let's make ours go clockwise. So if it's going this way, then the velocity would be straight down. Which way is the force?
That way. I learned that.
Force is towards the sun, and it's the gravitational force, right?
Yes.
Notice that these are perpendicular, so the gravitational force is only the centripetal force.
Yes, no friction.
Okay, no friction. Okay, here's your assignment. Okay, if you did not finish this up. And your assignment is to read this. Read all of it. It's not very long. Because we're going to rocket through circular motion on Wednesday.
Rocket through.
Rocket through.
Can I get a copy of one?
It's going to be a